possible. What you should do is that you should carry out a mathematical interpolation, isn't it? To fill these voids so as to get an analog signal. But are you sure that this signal that you obtained after mathematical interpolation represents the actual analog signal which was sampled? Are you sure about that? Or what?
No, sir. It
I
cannot
have
be
shown,
identical.
yes, I have shown in the next figure 4 analog signals. All right, 4 analog signals that have the same samples. So these are the 4 analog signals which, if you sample them, they will have the same samples. If you sample them at the same rate. So what's the way out? I have shown here 4 signals, 4 analog signals, but you can have infinite number of such analog signals whose sample data version will be same. All right. So what's the way out? The signal that you will get actually by mathematical interpolation, remember here that these signals marked in green, red, and blue, you can't get back these signals
Sir,
from the
sir,
sampled version, isn't it?
someone has
Yes.
started presenting. So can you just stop the presentation and start again? Someone had actually started presenting in between.
Where? Ask him
Sir,
to stop presenting.
yes, sir. He has stopped presenting, I think.
Okay. Is it visible or what?
No, sir, not yet.
Okay. Now it's visible, I think.
Yes, sir.
So yes.
Yes.
So these blue, red, and green, those signals you will never be able to get back from the sampled signal, because when you carry out mathematical interpolation, these undulations or oscillations, I should say, rapid change in between 2 adjacent samples, that information is not available to the mathematical interpolator. So the signal that you will get back from the samples will be the one with least possible oscillation. Apparently, it is this black signal, this signal. So this is the signal obtained by mathematical interpolation. All right. So that is the problem. Therefore, it is imperative that we should put some restriction on the sampling frequency. Why could the other signals could not be constructed from the sample data signal? Because those signals had high frequency components, all right, which could not be detected by these high frequency components, this oscillatory nature, that could not be detected by the mathematical interpolator. Therefore, some bound, or what should I say, restriction on the sampling frequency should be introduced, depending on the frequency or the bandwidth of the signal. That's what we want to study here. And we also want to study, if you sample at a frequency less than the minimum required, then what will happen to that sample data signal? What will it represent actually? So those are the things of, those are the issues of concern to us. So you can just write down here. So what I have written here, what I have stated already, in absence of any additional conditions or information, a continuous time signal cannot be unambiguously represented, specified by a sequence of equally spaced samples. Tau is the sampling interval or sampling rate, sampling interval or sampling period. I think it's done. So these are just 4 examples.
Sir, can you just go up once more?
Okay,
Yes, sir,
okay.
can you please show them?
Please tell me if you find any problem.
Okay, sir, thank you.
So I have only drawn 4 possibilities. There can be infinite number of such possibilities. You just draw them arbitrarily because those signals, they have nothing special. Only just ensure that the samples are all same for all these 3 or 4 signals.
Done, sir.
Therefore, the reconstruction of an analog signal from its samples, it becomes a problem unless some other information or restriction or constraint is available. Obviously, on the sampling frequency. Some minimum value of the sampling frequency has to be set. It will evolve out of discussion that we will have now. Sorry. CT stands for continuous time, and this hash stands for number. So that will be the signal obtained by interpolation, but it's not the samples could have been samples of infinite number of other signals that I have shown. So if you just carry out mathematical interpolation, that won't give you the true picture. আমাদের মধ্যে ক্লাস নিচ্ছি, পরে করবো। Is it done?
Yes, sir.
Yes, sir.
Now, because sinusoids are the building blocks for all types of signals, we want to develop certain insight into reconstruction of continuous time sinusoids from their samples. All right. That is the reason why we are considering sinusoids, because they will serve as the building blocks for periodic as well as for non-periodic signals. Right at the beginning, we just note an observation that I also mentioned when I dealt with that signal above. All right, the signal that I dealt with, the sample data signal, there I have already mentioned that in line with that observation, we may consider that if a uniformly sampled signal is obtained by sampling an analog sinusoid, it will also represent the sampled version of an infinite number of sinusoids of different frequencies. All right, that is one part of the story. Second is, if those samples, say if you are given the samples and you are told that these are the samples of an analog sinusoid, if you want to fit it to an analog sinusoid, those sample values, the one that you will get will be the sinusoid with minimum possible frequency, isn't it? Because as I have told you earlier, the intermediate undulations or oscillations in between two adjacent samples, that information will not be available. So just write down this one, then I'll proceed. Our further observations will be based on this fact. We will see how for different ranges of sample frequency, the sample data signal will represent what frequency of sinusoid. That we'll examine.
Sir, will you please explain this observation again? This one.
Okay, problem is, suppose you find that a uniformly sampled signal represents the sampled version of an analog sinusoid. And from those samples, if you are not given any other information, simply from those samples, if you are told that these are the samples of an analog sinusoid, get back the analog sinusoid. Can you do it unambiguously? You can't do that. It follows from the observation that I have made for that arbitrarily chosen sample data signal earlier. Okay, let me proceed. It will be clear to you. Have you written it?
Yes, sir. Done.
So we consider that we have an analog sinusoid xt it is sampled at a rate fs, all right, and the sampling starts at the instant t naught. For the sake of generality, I am considering that the sampling starts at the instant t equal to t naught. One thing is clear, that these are the samples, all right, these are the samples obtained. One thing is clear, if the sampling frequency is very large compared to the frequency of the analog sinusoid, then the samples, as we are finding here, then the samples will uniquely represent the samples of that analog sinusoid xt. But what will happen if fs is not very large compared to f? Or what is the minimum possible frequency with which the analog sinusoid have to be sampled so that the sample data signal preserves complete information about the original signal? That is our object of concern. Sampling frequency is fs, sampling interval is tau. These are the standard symbols that we are following.
Sir, can you repeat this part once more?
Which one?
This part.
Oh, xt is a continuous time sinusoid. I have shown only one cycle. You will have infinite number of such cycles. And we are sampling it. We are converting it into a discrete time signal by taking samples at intervals of tau. All right, at intervals of tau. So the vertical lines shown here, they represent the sample data version of xt. And I am assuming that the sampling starts at the instant t naught, not at the origin of time, not at t equal to 0, but at t equal to t naught. All right. We will see later that there is a certain effect of t naught also. If it is 0, something will happen for a particular frequency. If it is not 0, other thing will happen like that. Is it clear?
Sir, if the frequency will be high, then we can get the original signal back by
Yes,
interpolation.
unambiguously. There will be no problem. But you cannot do that. If you have some idea that this will be the maximum value of the frequency of the analog sinusoid that we want to sample, say if it is say 50 hertz, you cannot sample at a frequency of 100. Cannot means it is not desirable that to capture the complete information of a 50 hertz sinusoid, you will be sampling at a frequency of 100 kilohertz or 1 kilohertz. All right.
Yes, sir. Yes, sir.
Then the question comes that how should you decide what's the minimum frequency at which we should sample? That particular, what should I say? That particular information I am trying to retrieve from the discussions. Frequency of the sinusoid is f hertz or omega radians per second. A is the amplitude. T is time, capital T is the time period. I will start from a very low value of frequency, sampling frequency, and try to examine what happens. Then gradually I'll increase the value of sampling frequency and study what's the effect of increasing the sampling frequency. Sampling starts at a time angle. This should be time angle.
So can you go up once more?
Just 1 minute.
Yes, sir. Thank you, sir.
Now, on sampling the analog sinusoid, you get a sample data signal which I am representing in this way. X and tau. Simply in the expression for xt, I have replaced t with n tau. So that will result in a sample data signal, isn't it? So this x and tau will be a sine twice pi n tau by t, because I have replaced t with n tau. All right. So in this equation, if you replace t with n tau, you will get what is shown here, plus theta. Why does plus theta come in? Because when you will be starting the sampling, if I decide that I'll start the sampling at t equal to t naught, in a sampled version, if I represent that by x n tau, what will be the first sample? It will be the sample corresponding to n equal to 0. That is the standard convention. N equal to 0, the sample that occurs at n equal to 0, that is the first sample. You know that because we have started the sampling here at t naught, what is the first sample? It will be how much? A sine theta. So if you substitute n equal to 0 here, what will remain is x0 equal to a sine theta. That's why I have introduced theta here as the time angle. If you have any question,
Sir, we have only the sampled values. Then how we can assume sample data signal as a sinusoid only?
I couldn't get you. Please repeat.
Sir, we have only the sampled values. Then how can we assume the sampled data signal to be in sinusoid form only, just like a sine 2 pi n tau by t plus theta?
Yes, you assign different values to n equal to 0, 1, 2, 3, 4, etc. So x0 is a sine theta. All right. X tau is this sample. X2 tau is this sample. X3 tau is this sample. X4 tau is that sample. You understand?
So we are only having the discontinuous values, na data
Yes, that's
sampled.
I'm representing the discontinuous values. I have not used the symbol x tilde t. I am not using the continuous time mathematical model for the signal.
Oh, yes, yes.
I am representing that vertical lines. All right. That's what I am representing. Twice pi n tau by t is same as twice pi n f by fs, because tau is 1 by fs, capital T is 1 by f, where f is the frequency of the analog sinusoid. I have represented the ratio fs by f by the symbol epsilon. Fs by f by the symbol epsilon, that's what I have represented. So on making that substitution, I have obtained the expression for x and tau as shown here. Epsilon is fs by f or capital T by tau. Epsilon can be called the time period in terms of number of samples. How many samples are there in one complete cycle? Because it is T divided by tau, doesn't it show that epsilon is the number of samples in one complete cycle of the sinusoid? That's why we call epsilon the time period in terms of number of samples. I would like to point out one thing here. This determination of the minimum frequency that is required, this entire exercise, in almost all the textbooks, this entire exercise is done in the frequency domain. But in our department, since the introduction of this subject DSP, that was probably 25 years back, we have tried to explain this thing in the time domain, because we felt that in the time domain, if you make this explanation, then it's more easy to understand. We'll also dwell in the frequency domain. I'll later move on to the frequency domain also. But first I'll try to explain it in the time domain.
Done, sir.
Case 1 is when epsilon is very large compared to 1. That means sampling frequency is very large compared to f, implying that the sampling interval is very small compared to capital T. This situation I have already shown. There will be a large number of samples in every cycle. So it will not be a problem to get back the original sinusoid from its sampled version. But this is not a very desired case, because you will have unnecessarily large amount of data. So it requires unnecessarily large memory device to store this data. And when you carry out computations, you have to handle so many samples. Therefore, the computation time will increase, etc., etc. Large memory device means increased cost. This is the situation. Case 2. In case 2, I am straightway moving on to the case when epsilon is less than 1. That is, the sampling frequency is less than, I moved on to the other extreme. When the sampling frequency is less than the frequency of the analog sinusoid, or the sampling interval is greater than the time period of the analog sinusoid, what will happen then? Here, let me first show it. This was the original signal. I have considered only a few cycles of the signal, 3 cycles. Now, if you sample at a rate fs less than f, the sampling interval is greater than capital T. All right. So if the first sample is here, I have chosen one value of tau, which is less than capital, which is greater than capital T. Next sample, suppose it comes here. Next sample will come there. I mean, the time difference between those two, occurrence of those two samples obviously is tau. Again, this interval is tau, and so on. Now, I have considered only 3 cycles, and I have tried to feed these samples into a sine wave. So this is a portion of a sine wave shown by dotted line, isn't it? If I had considered several other cycles, more number of cycles, then what would have happened? I could have obtained a continuation of this dotted line representation. I could have obtained the entire complete cycle of this sinusoid, which is represented, part of which is represented by the dotted line. So doesn't it occur to you that ultimately the samples, they have lost the information of f, the sample of the original, the value of the original analog sinusoid, that has been lost. Now the samples, what they represent are the samples of a much lower frequency analog sinusoid, whose portion is shown here. All right. Therefore, if from the samples you want to use mathematical interpolation to get back an analog sinusoid, what will happen? You will get an analog sinusoid with very low frequency. What will be that frequency? That is the next question. Is it clear to you? If it's not clear to you, I'll tell it once more.
Sir, but this case is not useful for us, na, because we have completely
This
lost
case
the
is
original. Not useful for us because we have lost the original information of
that
original
is
signal
true,
X2.
but it may happen inadvertently. It may happen without your what should I say? Without your knowledge. Many times you may have an analog sinusoid whose frequency will be unknown to you, and you sample it at a rate that is less than the frequency of the analog sinusoid, and this thing will happen. That's why we want to study it. If you are not cautious enough, this may happen. You haven't
Yes,
written down this part, I think. Have you written it?
Settles.
Now
yes,
have a
sir.
look at this one. Draw it, then we have some mathematical derivations. This particular case, of all the cases, this particular case, that this will be dealt in details, and you have to understand carefully, very carefully. How will you find the sine wave which is represented by this sample data signal? How will you find this low frequency value? Say by mathematical maneuvering. Have you done it?
Yes, sir, done.
I had considered that Fs is less than F. Now, Fs is less than F means Fs is greater than 0, less than F. This subrange, I am splitting up into some smaller subranges. First, consider this situation that Fs is greater than F by 2, less than F. What will happen there if this is the situation? There is an important thing to note here is that I have not considered that Fs is greater than equal to F2, less than equal to F. I have not considered that. This is very important. I have considered the range as Fs greater than F by 2, less than F. What will happen under such a condition? What frequency of sinusoid will it represent? Just see here. Just compare with the original expression for x and tau, what I have done here. The original expression for x and tau was a sine twice pi n by epsilon plus theta. I have added twice pi n and subtracted twice pi n. That results in a sine twice pi n divided by times 1 by epsilon minus 1 plus theta. Now replace epsilon with fs by f. what do you get? F minus Fs divided by Fs. The original expression, from the original expression, what did you see? Xn tau is twice pi F by Fs n plus theta. Now here you have also shown that Xn tau can be twice pi n F minus Fs by Fs plus theta. That means Xn tau can be the sampled version of a sinusoid with frequency F minus Fs, which is less than F. All right. F minus Fs less than F. I am trying to locate what frequency values less than F can be represented by the sample data signal. Is it the only possibility, or there is something else also? Let us see. Okay, write down this thing, then I'll proceed. You can also maneuver x in tau in this way. Instead of adding twice pi n and subtracting twice pi n, what you can do is you can add 4 pi n and subtract 4 pi n. What does that result in?
-2.
Have you written it? It will become twice pi n f minus twice fs by fs plus theta. So these are the two possibilities. Those two frequencies are less than f. All right. If you just bring out a minus sign here, it is twice fs minus f. You have to convert it into twice fs minus f from f minus to fs, because this is negative and this will be positive. There is a phase change, and with that phase change, x and tau can also be the sampled version of a sinusoid with frequency 2fs minus f. So two possibilities, f minus fs and 2fs minus f. Which will be the one that will be represented by x and tau? It will depend on whether which one is smaller of those two frequencies, f minus fs and f 2fs minus f, which one is smaller, and that frequency will be represented by the sample data signal. So if you want to fit the samples into an analog sinusoid, the analog sinusoid that you will get will be one having a frequency either f minus fs or 2fs minus f, whichever is smaller. Because the smallest possible frequency will be the frequency of the analog sinusoid that you will get back from the samples.
Sir, can we add any other integer form like 6 pi n or 3 pi n?
Yes, you try
No,
out with 6 pi n. If you try out with 6 pi n, what will happen is that for this particular subrange, you will get that the negative values that you will, this frequency values that you will get, they will turn up to be negative. So that is not possible for this subrange. We will do that for other subranges. All right. Not
Yes,
for
sir.
this subrange. for a given f, for a given f. I hope you have written down the expressions. So for a certain f, depending on the exact value of the sampling frequency of these two frequencies, any one can be smaller. So we say that the alias of f, this is the term that is used. You know the meaning of alias. The alias of f is either f minus fs or 2fs minus f, whichever is smaller. That this sample data signal is not preserving the frequency information of the original analog signal, this phenomenon is called aliasing. Phenomenon is called aliasing, and aliasing is the result of undersampling. What is meant by undersampling? Sampling at a frequency that is less than the minimum required. Sorry. For f is less than f by 2, just 1 minute, what I have written. Yes, if fs is greater than f by 2, if fs is less than f by 2, then using these expressions, you will find that the frequency information that you will get, that will turn out to be negative. So for fs less than f by 2, what will happen? This analysis will not be valid. You have to go for some other. Now I am considering fs greater than f by 3, less than f by 2. Why greater than f by 3? That also will be clear to you. Now come to the case for fs greater than f by 3, less than f by 2. What I do here is that I am adding 4 pi n and subtracting 4 pi n. That results in an expression of the form a sine twice pi n f minus 2fs by fs plus theta. So for this subrange, it is clear that one of the possible frequencies, one of the possible aliases of the frequency f is f minus twice fs. The other possible alias will be if you just, instead of 4 pi n, if you add 6 pi n and subtract 6 pi n. Then you get here minus a sine twice pi n, 3fs minus f. All right. So these are the two possible cases. Either f minus 2fs or 3fs minus f. Whichever is smaller will be reconstructed from x and tau.
Sir, sir,
Hmm.
sir, if fs is less than f, then how can f minus fs be negative?
Which one?
Sir, above, okay, scroll up where you wrote that alias of f is, yes, yes, yes. Sir, if fs is less than f by 2, then how can f minus fs be negative?
What will happen here?
Sir, no, this term will be negative, but
That is the reason. That is the reason. That's what I have stated. This term will be negative. So
F
you
minus
cannot
Fs
get
will
any.
be positive, I think. F minus
F
Fs will be
minus,
positive for the condition. F by 2 greater than Fs.
If fs is f by 2, then it's 0.
Sir, f minus fs will always be positive because that is the initial condition. The
Yes.
other one will be negative.
Yes,
This one.
The first frequency, sir. F minus Fs.
yes,
That
yes.
one.
This will be the
Hmm.
always positive.
Yes.
Because that is a bound. The second one will
No.
be negative.
No. You remove this line. Sorry. There is problem. Problem is that if you move on to fs less than f by 2, these two frequencies are not the smallest frequencies that you have. You can come up with still
Smaller
smaller frequencies, as I am doing now here. All right. As I am doing here, you will get still smaller frequencies. F minus 2fs or 3fs minus f. Yes, only the second one would come up as negative. Problem with first one is that that doesn't give you the minimum possible frequency. Have you written it?
Yes, sir.
Yes, sir. answer.
I hope you have written it. Now have a look at this numerical illustration. Now, suppose you have an analog sinusoid with frequency 300 hertz. Now, if Fs lies in the range, it is between f by 2 and f by 3, that is between 150 hertz and 100 hertz. All right, 100 hertz and 150 hertz. What will happen then? Suppose the sampling frequency is 110 hertz. Then f minus 2fs will be 80 hertz and 3fs minus f will be 30 hertz. So which one will be the alias of f? Obviously the lower one. So alias of f in this case will be 30 hertz. So that frequency of 300 hertz has been aliased into a frequency of 30 hertz. So from the sample data signal, the sinusoid that you will be able to recover by mathematical interpolation will not be a sinusoid with frequency 300 hertz. Instead, it will be a sinusoid of frequency 30 hertz.
স্যার এটা একটু নিচে করে উপরটা একটু লেখা হয়নি স্যার।
এটা
ইয়েস স্যার, কোশ্চেনটা
কোনটা বলছি?
না স্যার, এই যে নিউমেরিক্যালের যে কোশ্চেনটা স্যার, নিউমেরিক্যালের যেটা ছিল। হ্যাঁ স্যার, হ্যাঁ স্যার, এটা থ্যাংক ইউ থ্যাংক ইউ।
Consider another value f is equal to 145 hertz. Under that condition, what will be the frequencies f minus 2fs and 3fs minus f? 2fs is 290 hertz, f is 300 hertz. So f minus 2fs will be 10 hertz. 3fs means how much? 290, 390, 435. 435 hertz is 3fs minus that 300, 135 hertz. All right. So here the alias of 300 hertz will be 10 hertz in this case. Written it.
Yes, sir.
Done.
you need not write this sub-range. I am just explaining, it will be clear to you. When fs lies in this range, f by 4 to f by 3, what will happen? The minimum, to obtain the minimum frequency, x in tau, in the expression I am adding 6 pi n, subtracting 6 pi n, thereby getting a sinusoid with frequency f minus 3 fs. If instead of 6 pi n, you insert here h pi n in both these cases, you would have got a sinusoid with frequency 4 fs minus f. So for that particular subrange, what will happen? The alias of f will be either f minus 3 fs or 4 fs minus f, whichever is smaller. এটা আর লেখার দরকার নেই। From the earlier two cases, it's evident. Now we can just generalize. All right. I am still confining my attention to fs less than f. So for such a range, fs greater than 0 less than f, if fs is greater than f divided by k plus 1 less than f divided by k, where k can take on values of 1, 2, 3, etc. All right. In this subrange, what will happen? The smallest frequency sinusoid, which is represented by x and tau, it will be either f minus k fs or k plus 1 fs minus f, both of which are less than small f. All right. Therefore, depending on the value of fs, or we may say the relative values of fs and f, for that particular subrange, the original range was fs greater than 0 less than f. We are considering this particular subrange. So the two possibilities are having f prime equal to f minus k fs less than f, or f prime equal to k plus 1 fs minus f less than f. Which one will be considered as the alias, or which one will actually be the alias? That will depend on which one will be smaller. So from x and tau, the analog sinusoid that you can reconstruct will be up either f minus k fs by f minus k fs or k plus 1 into fs, whichever is smaller. So this phenomenon, as I have mentioned, this is called aliasing, and it is the effect of undersampling, sampling at a rate less than the minimum required. Have you written it?
Yes, sir.
Now, need not write this thing, but in all these cases that I have considered, you could also show that x and tau can be the sampled version of frequencies that are greater than f. But we are not interested in that because those frequencies will not be reconstructed. Only frequency that will be reconstructed will be the one will be with the minimum value. That's why I have not considered that. Now move on to the next case. When Fs is exactly equal to f. Fs is exactly equal to f means tau is equal to capital T, epsilon is 1. Then x and tau will come out as, if you substitute epsilon equal to 1 in the expression for x and tau, you will find that x and tau will come out as a sine theta. For all values of n, x and tau will come out as a sine theta. That means what information will the x and tau represent? It will represent a DC signal. If all the sample values have they are same, then obviously x and tau will represent the samples of a DC signal, isn't it? As I have shown there, all samples will be equal. So it's a DC signal that is represented by x and tau. So then f is aliased into a frequency of small f equal to, the frequency of f prime equal to 0. Here one thing is also important. Now have a just refer back to the sampling instant where we started. This is the instant t0, small t0. If I had started the sampling at 0 crossings, what would have happened? All sample values would have been 0. If I had started the sampling at any one of the 0 crossings, then what would have happened? All sample values would have been 0. So sampling at 0 crossings yield no information. If Fs is equal to f and the samplings take place at 0 crossings, then at the output you don't have any information. It's 0. All the sample values will be 0. That is the case for f is equal to f. Now, after we consider that case, we have an important observation to note. What is that observation? I'll come back here. If In general, Fs is equal to small f by L, where capital L can take on values of positive integers. Then what will happen? F by L means if L is 1, Fs is f. If L is 2, Fs is f by 2. If Ls is 3, Fs is f by 3, and so on. If that is the case, then tau, the sampling interval, will be L times the time period. Then what will happen to x and tau? You substitute here L, what will happen? X and tau will come out as A sine theta. So reconstruction will be DC signal. And obviously samplings at zero crossings yield no information. Just refer back to what I have pointed out when I was discussing about Fs greater than 0, less than f. I have pointed out that I am not considering Fs greater than equal to f by 2, less than equal to f by 3. All right. I am not considering that. Less than f, sorry. I am not considering that. Why that equal to is not coming? Because equal to is a special case. And that's why I have dealt with it here. General observation. We have completed it. Now come to this case. Have you written it?
Yes, sir.
Move on to the next one. Fs lies in the range f and 2f, in between f and 2f. All right. Not greater than equal to f, less than equal to 2f, but Fs is greater than f, less than 2f. So tau lies in this interval, t by 2 to t. When that is the situation, what do we observe? I have considered an arbitrary case where tau is greater than t by 2 but less than capital T. And these samples, I have tried to fit them into a sinusoid. So the sinusoid that I wanted to fit them into is represented by, portion of the sinusoid is represented by this dotted line. So here also you can see that the information about the original analog sinusoid is lost. So x and tau represents the information of a much lower frequency sinusoid. What will be that frequency? It will simply be Fs minus f.
Done, sir.
I have added twice pi n and subtracted twice pi n to yield, to get it as minus a sine twice pi fs minus f by fs into n minus theta. So x n tau can represent a sinusoid with frequency fs minus f, which is less than f. Can you carry out mathematical maneuvering to show that x n tau can represent sinusoids of still lower frequencies than fs minus f? You can't do that. You try out, but you will find that this is the frequency fs minus f. That will be the alias of f. You cannot come across still come across frequencies that are less than fs minus f. So here fs minus f is the alias of the original frequency small f. So here also we still have undersampling. And aliasing is there.
Done, sir.
Therefore, x n tau is also the sampled version of a sinusoid with frequency f prime, which is fs minus f less than f. So here also you have a phenomenon of aliasing.
Done, sir.
What will happen if you sample at a frequency fs equal to twice f? That is important. Why it is important? Because in almost all the textbooks you will find that the minimum sampling frequency for such a case is fs equal to twice f. But what will really happen when fs equal to twice f? Let's see. Write it down, then I'll proceed to the next case. Fs equal to twice f. Fs equal to twice f means tau equal to capital T by 2. Now I have used here a phrase, frequency f of original signal is folded back into the interval f prime greater than 0 less than fs by 2. The exact implication of this term folded back, it will be clear to you when we just move on to the frequency domain. When fs is equal to twice f, what will happen if you substitute epsilon equal to 2 in the expression for x in tau? It will come out as a sine pi n plus theta. That means x in tau, it will be a sine theta for even n, and it will be a sine minus a sine theta for odd n, isn't it? So alternate samples will have same magnitude but opposite sign. As a consequence, what will happen is that the frequency information of the original analog sinusoid will be preserved here. The frequency information is preserved. But you will find that the amplitude and phase information, they are not preserved. What I mean here is that x and tau can also be represented in this manner. It was a sine pi n plus theta. Instead of that, x and tau can also be represented by b sine pi n plus alpha. That is b sine twice pi n by 2 plus alpha, such that b sine alpha is equal to a sine theta. And there can be infinite number of combinations of a and theta, b and alpha, for which, infinite number of combinations of b and alpha, for which this equality will be satisfied. Therefore, if you sample at a frequency fs equal to twice f, although the frequency information is captured, it's preserved, but the amplitude and phase information is not preserved. Hence, this also is not a proper frequency. You can also understand in this way. Say this is the expression for x and tau, pi a sine pi n plus theta. What would have happened if you started the sampling at some zero crossing? What would have happened? All samples would have been zero, isn't it? So that would have yielded no information. That's why this frequency is not a proper frequency.
Done, sir.
Sorry.
Done, sir.
I have shown here two possible reconstructions. One is that shown by dotted line, very faintly drawn, and the other by the firm line. Enlarge. Next is the last one. Now in case 5, also note that if theta is 0, that means if samplings take place at 0 crossings, that will yield no information. I have missed it, I have stated it verbally, but I haven't written it down here. All samples will be 0 if the samplings take place at 0 crossings. Last case is for fs greater than fs greater than twice f. When fs is greater than twice f, you will find that under that condition, the original analog sinusoid can be uniquely recovered. Because when fs is greater than twice f, if you carry out mathematical maneuvering in the same manner as I have did for these cases, you cannot land up with an expression for x and tau from which you will be able to point out that x and tau can also be the sampled version of a lower frequency sinusoid. You cannot get such an expression. Only thing that you can get will be x and tau if fs is greater than twice f. X and tau can be the sampled version of sinusoid with frequency f and higher frequency sinusoids, which is also the case for others. But there, a lower frequency sinusoids rather, and higher frequency sinusoids. But for f is greater than twice f, only higher frequency sinusoids having frequency greater than f. Therefore, in such a case, the original analog signal will be uniquely recovered. So just see here, what I have shown here is that x and tau, which is the sampled version of a sinusoid with frequency f, can also be the sampled version of analog sinusoids with frequencies mfs plus f, where m has values of 1, 2, 3, etc. That is not the only possibility. There can be still, other types of higher frequencies also, but no low frequency sinusoid. No sinusoid having frequency that is less than f. So after you write down this, I'll complete for today. X and tau can also be written as minus a sine twice pi mfs minus f times n by fs minus theta, m having values of 1, 2, 3, etc. These frequencies are also greater than the frequency small f. So here there is no question of aliasing. F doesn't fold back into a lower frequency.
Answer.
Sorry. But now, if I, for a given frequency of sinusoid, if I tell you the sampling frequency and say there is aliasing, can you find the aliased frequency? You should be able to find it out, proceeding in a manner that I have stated. But if you have an exam where the questions of the MCQ variety, you cannot work it out. It will consume much more time. So what is the general expression for aliased frequency? That is noted at the last point, perhaps. And this is the expression. If sinusoid of frequency f is sampled at a rate fs less than twice f, the alias of f is mod of magnitude of nfs minus f. All right. What is capital N? Capital N is the value of an integer for which this nfs minus f has minimum value. You can try it out. Consider a small f, consider different values of capital Fs, different values of Fs, and then try out using this expression. Therefore, if a sinusoid is sampled, analog sinusoid is sampled only at a frequency greater than twice its frequency, then only from the sampled version, the original analog sinusoid can be recovered without ambiguity. That is what we have observed here. We have also studied the phenomenon of aliasing, which is the effect of undersampling. Okay, so we'll meet another day. You talk among yourselves and let me know. All right.
Okay, sir.
So I am just closing it, winding it up. Is that all right?
Yes, sir.
Yes, sir. Thank you.
Yes, sir.
Thank you. Thank you very much.